Today we're going to look at section 3.7, related rates, and that's a tough one. Related rates is how we look at different rates of change and how they are connected together. So in real life we often just naturally assess different rates. For example, if you're crossing the street and you're seeing that a car is approaching from afar, you're going to be thinking of your velocity, how fast can you cross the street, and how fast is the car coming. It's a different rate. And are you going to be able to cross the entire road before the car is there, or should you wait until the car passes? So these are two different rates of change that you are kind of working together in your head to see how the situation is going to develop. Remember that velocity is a rate of change. It's the rate at which position changes. So if the velocity of a car is really large, very high, very fast, that means the position is changing quickly. So this is going to be a section that you're probably going to find very difficult, and it's based on a lot on word problems, which of course makes it even harder typically for students, but we'll see a couple examples. We're not learning anything new really here, we're just really trying to apply things that we've learned in previous sections to real-life problems. Okay, so the note just states that when we talk about a rate of change at a point, it means the instantaneous rate of change. When we say velocity, it means instantaneous velocity, not average velocity. So firstly, an example that is not real life, but it's going to help us kind of start thinking about related rates. So related rates means that two rates are different, but they are connected somehow. We'll see some examples as well. Suppose x and y are both differentiable functions of t, and they are related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. So we have two rates here. We have dx dt, and we also have the rate dy dt. So these two rates are different things. It's how much x is changing. This one is how much y is changing. And they are related because we know that y is always equal to x squared plus 3. So they are connected by this equality here. We can take the derivative of this. It seems like a great idea. We have y, so if we take the derivative, we're going to find the derivative of y, and here we have x, and that's going to be really nice because dx dt is the derivative it's going to be given. What's new in this section, as you can see, is we are taking the derivative in terms of t. That's going to be a big leap. We'll see how it works out. Derivative of y is just dy dt. Derivative of x squared is 2x, but we are differentiating in terms of y. That's why it says dy dt. Sorry, we are differentiating in terms of t. That's why it says dy dt, not dy dx. That means x is not the privileged variable we are differentiating with, and therefore when I take the derivative of x squared, I need to do 2x times the inside derivative, which is dx dt. From here, I'm lucky, I have everything. I know that x equals 1, I know that dx dt equals 2, and so I can plug stuff in and find that dy dt is equal to 4. So let's talk a little bit about related rates in real life examples. Here you have an example that you can find on GeoGebra of a ladder, and as it moves, we're going to talk about two different rates. Which ones? We're going to look at the rate. Oh, first of all, there's a question here that you could do if you go to GeoGebra, but we are going to talk more about just the situation that is discussed here, more than solving this precise exercise. If you look at the rate at which A changes, the position of A, so A is moving as the ladder slides down the wall, you will notice, hopefully, that A is moving at a constant rate. the velocity of A is constant. It's not going faster in the beginning or faster in the end. Let's bring it back and just observe that A is moving constantly. Right? Never faster, never slower, until the ladder touches the floor. Now, if you look at B, you're going to see something very different. In the beginning, B barely moves. It really doesn't move fast. And now it's going faster, and now it's going faster and faster and faster and faster. And in the end, it's really fast. So I can show you that just by showing you, if I go A from 0 to 1, observe point B. B barely moves at all. So the velocity of B is very, very small. On the other hand, later on, when the ladder is almost at the floor, if I move A from 9 to 10, which is the same increment of 1, what happens to B? B moves enormously. The velocity of B is huge at that point. B moves from 4 point something all the way to 0. So the rate of A and the rate at which B changes are related, because B entirely depends on where A is and how fast A is moving, but clearly they are not proportional. So don't confuse the idea of proportional rates with related rates. In fact, to show how different A and B are, you could realize that A is a positive rate because A is moving to the right. On the other hand, B is going down, so the rate of change of B is actually a negative number. So they're very, very different. Still, they are related. So here's the example we are going to work with. Air is pumped into a spherical balloon at a rate of 0.5 cubic meters per minute. Find the rate of change of the radius when the radius is 2 meters. So we have a big balloon, we're pushing air in at a constant rate. So this hand is just moving down constantly. It's pushing air constantly, and that constant rate is 0.5 cubic meters, so half a cubic meter every minute. It's just going in constantly. At what rate is the radius changing when the radius is 2 meters? If you think for a little while, just of your personal experience of blowing balloons, you may realize that in the beginning, when you blow a balloon, it grows very quickly in the beginning, and then it starts to seem to grow slower later. The volume is growing at the same rate, but the radius kind of changes less and less as you put more and more air in the balloon. So these two rates are related, but they are not proportional or anything. So notice that we don't have any formula here, and this is one of the reasons why it's more difficult. We have to figure out which formula from mathematics from previous classes we need to use. And in this case, we are talking about the radius of a sphere. It says that it's a spherical balloon, so it's a good idea to write the volume of the sphere. V is 4/3 pi r cubed. And we're going to take the derivative because we have lots of information about rates. We are also looking for a rate. So taking the derivative is going to bring us in that realm of rates. The derivative of v in terms of t is dv dt. And on the other side of the equal sign, the derivative of 4/3 pi r cubed is going to be 4/3 times pi times 3r squared. Right? R is a variable, so it becomes 3r squared. But we need to multiply by the inside derivative, because r is not the privileged variable of differentiation. And now let's try to plug what we know. We know that dv dt, the rate of change of the volume, is 0.5. We know that the radius is 2, and we are looking for dr dt. So from here, it's simple algebra to figure out that dr dt is 1/32 pi. And what are the units? Well, you have to look at the top and the bottom here. R is a radius, so it's meters, and T is a time, so it's minutes. Meters and minutes. What is the units of dv dt? It's a volume over a time, so it would be cubic meters over minutes. Cubic meters per minute was given there. So the important note, the volume increases at a constant rate, but the radius increases at a variable rate. They are related, but it's not because one is constant that the other one is going to be constant as well. The rates are related, but it doesn't mean that they are proportional. All right, second and last example in this difficult section. Find the rate of change in the angle of elevation of the camera shown in the figure. Here's the camera down here. 10 seconds after liftoff. The position equation is s equals 50t squared. So there's a shuttle here that starts on the ground, and it goes up, and the position after 1 second you could calculate by plugging t equals 1, and you would find that s is 50. It looks like the units are not specified here, but we can see here that it's 2000 feet, so the units of distance are feet. Alright, so after 10 seconds, it's interesting to know how high this shuttle is, and we plug in t equals 10, and it gives us 50 times 10 squared, 5,000. So at that point, the shuttle is 5,000 feet in the air. We can use this equation as well to find more information about the rates. If we take the derivative of this, we will find ds dt equals 50 times 2t, which is 100t. We don't have to multiply by the inside derivative because basically it's dt dt, so it doesn't matter. That allows us to find that ds dt is 1000. I could have put units here, it would be 1000 feet per second. That's the velocity of the shuttle at that moment. Secondly, because we are wondering about the angle of elevation, and this means the angle here, so we're wondering how fast is the camera changing its angle to follow the shuttle. In the beginning, you may realize that when the shuttle moves a little bit, the angle changes quite a lot. But now can you imagine the shuttle being like 3 A4 papers up? Then it would be so far up that the angle of elevation of the camera wouldn't change very much anymore. It would already be almost vertical, and there's not much wiggling of the camera anymore. So we need to find a relationship between theta and s. This is an s. And a good one to choose is tan theta equals, its tan equals opposite over adjacent, so s over 2000. We also know that tangent theta is s over 2000. So we can calculate theta. It gives us the information that theta is 1.190 radian, and we can also take the derivative of tan theta equals s over 2000. What is it? The derivative of tan theta is secant squared theta times the inside derivative here. Secondly, notice how this is a quotient, but you shouldn't be fooled. You could use the quotient rule, but you would just make your life a lot more complicated than it needs to be. This s over 2000 just is a linear function. It's 1 over 2000 times s. And it's so much easier to take the derivative like that. What's the derivative of 1 over 2000 s? It's 1 over 2000 times s becomes 1 times ds dt. And so plugging in the information we know, we can find d theta dt equals 0.069 radians per second. So this is a copy of my notes, and I happen to have done everything in order, and everything fell into place perfectly. We calculated theta, and it was something we needed later. The reality of you and me solving exercises for the first time is kind of trying stuff, and you may start by figuring out that tan theta equals s over 2000, and then you're kind of stuck because you don't know what to do with that, and then you go here and you use that for the derivative. So things might come in a completely different order. You have to be able to accept that and just gather information, find the derivatives, and gradually you will reach the answer. It may not be a nice linear process here, like me, in just like 4 lines, 5 lines, I get the answer. It may be a lot of squiggling and a lot of mistakes, but just work with the information you have and use the tools we've learned, and hopefully you reach the answer at some point. Thanks for listening to this, and take care.